about debris disk, we have two very nice talks. They're going to be summaries of the full talks that are on the YouTube channel. And the first one is Mark Wyatt from the University of Cambridge. So Mark, whenever you want, floor is yours.
Okay, thank you, Isabel. And thank you to the organizers for inviting me to give this talk, which is going to be on the theory of debris disks. And there's a companion talk in a minute by Alycia, who will talk about the observations. And what I'm going to be talking about is how we can use those observations to tell us something about planetary systems within which debris disks reside. So first of all, let's get on the same page about what a debris disk is, seeing as we've been talking about protoplanetary disks until now. So the perspective that I'm going to be using in this talk for debris disks is that they are a component of a planetary system. They are anything that is in a planetary system that isn't a planet. So, for example, in the solar system, we have the comets orbiting the sun beyond Neptune, and we also have the asteroid belt orbiting much closer in, as well as any of the dust and gas that comes from them. And the picture we built up from observations of debris disks over the years is that many stars, many nearby stars, have Kuiper belts, like belts of planetesimals at tens of AU. They also have a halo of small dust extending beyond that. They may have planetesimal belts in their asteroid-like zones. They may have dust in the habitable zones, and interspersed within these dusty regions are putative planets. And we can tell something about the existence of these planets, because if there are planets that are in the disks, then we know that they will impose structure on the debris disks. And the purpose of this talk is to tell you how they'll do that. But first of all, we need to have a primer on what some of the physics is that's going on in a debris disk. So let's start off with a simple model where we've got planetesimals orbiting the star in a fairly narrowly confined belt. The planetesimals will just continue orbiting the star, and the thing that will stop them is if they collide with another planetesimal that will break them up into smaller fragments that will then orbit the star until they collide with other fragments that then go on until they collide with smaller fragments. And the result of this is what's called a collisional cascade, where big objects are getting broken up into smaller objects that are getting broken up into smaller objects, and so on down to dust. And the characteristic size distribution you get out of this, this process is one in which most of the mass is in the biggest objects and most of the dust, and most of the cross-sectional area, which is what you see, is in the smallest dust. Now, the very smallest dust, below around a micron in size, is blown out by radiation pressure, by the interaction with the stellar radiation as soon as it's created. But even for dust that is just above this blowout limit, which is that which has most of the cross-sectional area, which is most of what we see, it is affected by radiation pressure, and which puts it onto these highly elliptical orbits that cause this halo that I was just talking about, just outside the planetesimal belt. Now, there's a whole bunch of other physics that could be going on in a debris disk, but this is enough to be getting on with. Of course, the main perturbation I'm going to be talking about to this scenario is planets in this talk. Before I do, though, a brief word on how we model debris disks, because it should be pointed out that we don't have one model that can encapsulate all of that, those physical processes. It's quite a complex problem. There are two types of approaches. You can either follow the individual particles, in which case you can follow their dynamics very faithfully, but you find it hard to model how collisions pass mass between things of different size. Or you can follow the phase space, in which case you follow the density of particles in different parts of phase space, in which case you can pass mass between different size bins and follow collisions faithfully, but the dynamics is not so faithfully reproduced. And I'm not expecting you to understand the distinction between these in this talk. It's just to point out that there is not going to be one model that can explain everything. And if you see a theoretical result, then it will likely take on a subset of physics and be applicable to a certain type of observation. I can also use this as an opportunity to highlight the hands-on session on disk models, because what I'm going to be talking about is the structure of the disks, and there has to be a second step, which is the radiative transfer, that tells you how that structure would manifest itself in observations. And if you go to the hands-on session, then you'll learn about tools like RADMC 3D that can that does that translation. So how do planets perturb the orbits? Well, we have mathematically it's split into 3 different types of perturbations. You've got secular perturbations that are exactly equivalent to spreading the mass of the planet around the wire described by its orbit and affect everything in the disk. We've got the resonances, which are specific, affect particles at specific locations where their orbital periods are a ratio of 2 integers times the orbital period of the planet. And then you have scattering, which is applies to particles that are unfortunate enough to come close to planets, so they have a close encounter. So what do secular perturbations do to the planetesimal disks? Well, this panel here on the left shows the structure of a disk 100 million years after a Jupiter-like planet forms within it, close in here. You see this tightly wound spiral structure that propagates through the disk, and very close to the planets, this spiral structure becomes wrapped, and the orbits of the neighboring planetesimals can start colliding and creating the dust. This inner edge is also eccentric, which means that the star is no longer at the center of the disk. And if the planet is inclined to the disk, then you also get a warp propagating through the disk. If the planet is very inclined to the disk, then you can get something that is slightly counterintuitive, which is a disk that is no longer coplanar with the planet's orbit, but is actually orthogonal to the planet's orbit, which is here in this image. If we have a multiple planet system, then you can get what are called secular resonances, and those can carve gaps in a broad disk. And you can get these gaps not only if you have a multiple planet system, but if you have a single planet system and a massive disk. And of course, if we see any of these structures, then we can use that to infer something about the planets that could be causing it. And indeed, that was what was used. It was the warp in the Beta Pictoris disk that was used to infer the presence and the properties of the planet that we now know as Beta Pic B, that has since been imaged. Okay, so that's the structure of the planetesimals. It's worth pointing out that if you look at the dust that is affected by radiation pressure, then that could look slightly different. And you can get a range of different types of structures, even from a relatively simple model. So this, for example, shows if you have an eccentric ring of planetesimals, what it would look like in different observations. If we have a low resolution observation, you see two of a fairly inclined edge on eccentric ring, then you see 2 lobes, one of which will be brighter than the other. And there's some discussion over which one would be brighter, the pericenter side or the apocenter side. If you look at the dust that's in the halo that extends beyond the planetesimal belt, then you can get a whole range of structures that depend on the viewing geometry relative to the disk. The mean motion resonances can be both bad and good. One example where they can be bad is close to a planet, because although the resonances are fairly narrow in range, they have some finite width, and close to the planet they all start overlapping, which causes a gap to form along the planet's orbit. For example, this is the distribution of planetesimals after a planet is introduced at 50 AU, and you can see this the width of the gap and also the shape of the gap depend on the planet mass. So small mass planet carves a narrow, sharp gap, and a high mass planet carves a wide and shallow gap. So the idea is that we can use the shape of a disk's inner edge to tell us something about the planet that is causing it. Mean motion resonances can also be unstable at on their own at specific locations, particularly if the planet has a moderate eccentricity, and this could be a way of feeding in exocomets into the inner regions of the system. Okay, mean motion resonances can also be good. So we see planetesimals in the Kuiper belt trapped in resonance with Neptune, and this is because Neptune migrated outwards, and as it did so, its resonances swept through the primordial Kuiper belt, trapping planetesimals in resonance and then migrating out with Neptune. And because of the special geometry of resonances, then you find that the distribution of planetesimals becomes clumpy as a result of that. So this means if we observe clumps in disks, then we can use those clumps to tell us something about the existence of the planet, but also its mass and its migration history. Okay, scattering, the most obvious consequence of scattering is removal of material. Things get ejected from the system, and you can use the fact that planetary systems, these debris disks have these cleared inner regions to tell something about the planets that must be there to scatter out all of that material that might have been there originally over the age, given the age of the system. There's a couple of papers here that have done that. But another thing that scattering does is not just remove material, but on its way to being removed, it radially transports it. So for example, comets in the solar system start out in the Kuiper belt, and then they get scattered amongst the outer planets before they make it into the inner solar system, where they can deposit their dust that can then feed the zodiacal cloud that we see. And the hope is that we can use observations of exozodiacal dust to inform on the kind of planetary system that is scattering comets, exocomets inwards to cause this. But the explanation of exozodiacal dust does not necessarily require exocomets. It does not necessarily require planets to be causing it, because we also have another mechanism, which is Poynting-Robertson drag, that can drag dust in from an outer belt. Now in the solar system, this is actually a dominant mechanism. So dust makes it all the way in from the asteroid belt all the way into the sun without suffering a collision, which means you get a filled in a region. But in the extrasolar systems where we see debris disks, these are necessarily very dense because they have to be bright enough to detect. And this means that the dust doesn't migrate very far before suffering a collision and getting destroyed. So you end up with these very cleared inner regions that we see. Now they might be cleared, but actually they're not completely empty. And the amount of dust that we get in this inner region is actually now known to be detectable. So this plot on the right shows what the models predict for the null depth we expect in nulling mid-infrared interferometry from observations of stars that have outer belts. And this null depth is between 0.1 and a few %. And it's very comparable with the levels that have been observed. And the fact that we could be seeing this dust that is in the middle of a planetary system gives us a very powerful diagnostic of the planets. For example, this is a simulation from Chris Stark that shows dust created in a planetesimal belt out here. As it migrates inwards, it gets collisionally depleted. But when it encounters a planet that is here, some of it gets trapped into resonance, causing these clumpy structures here. And when the dust falls out of resonance at the end, it then gets ejected by the planet. So you then get this large inner hole here. So if we saw an image that looked like this, we would be able to tell a lot about its planetary system from this, which is a good thing. Of course, it's also could be a bad thing if we wanted to try and detect planets that were sitting there, because they're sitting next to dust that can act as noise. Okay, so that's it from me. I guess the brief summary is that there's a whole host of structures that you see. And in fact, those are the structures that are also seen in observations, which is a good point to turn over to Alycia, I think.
Yeah, so now it's the turn for the theoretical part, right? Oh, no, for the observational part, sorry. Yeah, whenever you want, Alycia.
Okay, great. You can hear me okay? You can see the slides? All right. So great. Thank you, Mark. That set up this beautifully. I am happy to be with you today, and thanks to the organizers for having me. So I'm going to tell you a little bit about the observations, and I encourage you to look at the full-length talk on the YouTube channel. So in this talk, I want to concentrate a bit on the process of how we observe disks, the actual mechanism by which we make the observations, which I didn't talk much about in that recorded version. So look at the recorded talk for more about what we have actually observed. So there are two main ways that we observe disks. The first one is looking at them in scattered light. So in this image, you're seeing the disk in our own system, the zodiacal light, and the sun is below the horizon, but these dust grains above our horizon are acting as small mirrors, reflecting the light of the sun back to us. So that's the same as when you see dust glinting in your window if you shake a blanket in it in a sunny day. So dust grains scatter light most efficiently at wavelengths that are about their own size. So if we're observing scattered light at visible or near infrared wavelengths, we're mainly looking at dust grains that are about a micron, maybe 10 microns in size. The good thing about observing scattered light is that dust grain scattering doesn't depend on the temperature of the grains. So you can see grains wherever they are as long as there's enough starlight. Of course, the starlight falls off as 1 over the distance squared as you move away from the star. Dust scattering also depends on the composition and the structure of the dust grain. So you can use the amount of scattered light as a function of wavelength to infer something about the composition of the parent body, such as whether it has a lot of organic molecules, which tend to make less scattered light, or a lot of volatiles, like a comet that makes a fluffy grain, or an asteroid-like grain that's compact. The other advantage of using scattered light to observe disks is that the diffraction limited resolution of optical and near-infrared telescopes is very high. So until the advent of ALMA, the highest spatial resolution that we could get for looking at disk structure came from scattered light observations. So, and it's in fact still true that a 10-meter telescope operating at 1 micron has 20 milliarc second spatial resolution. So that's still better than what ALMA can do in the far infrared. So how do we actually observe this scattered light though? Because the problem is, of course, that we have the star there. And in order to actually use that spatial resolution, we have to remove the starlight. So we have two basic ways of doing this. We can either go to a very stable telescope, such as a space telescope, the Hubble Space Telescope, JWST should be just as good. And we can subtract the light from a reference star that doesn't have a disk. So you don't know it here, but you're looking at an image of a star with a disk. You can't see the disk because of all that light from the star, even though the star is placed behind a coronagraphic bar in this image. So if we also observe a star without a disk, we can subtract those two images, and Hubble is stable enough to allow us to do that. We of course have to scale the reference star to the brightness of the star. We also, it's not perfectly stable, so we have to move things around a little bit to align them. But now you can see the disk peeking out now that we've subtracted away the starlight. And you can do this at multiple orientations of the disk or the telescope with respect to the disk to try to get rid of the coronagraph and the diffraction spikes and wind up with a final image. So this is HD 181327. So, disks are the most challenging application of high spatial resolution imaging, because although the techniques that we use are similar to the techniques for imaging planets, disks can fill the space around the star with an unknown geometry. When you're looking for a planet, you're looking for a point source. But when we're looking for a disk, we don't intrinsically know the geometry or the inclination of the disk to our line of sight. So it's a much more challenging application of these kinds of stellar removal processes in the observing even than exoplanets are. So to do this on the ground, we have yet another challenge, which is of course the Earth's atmosphere, where we have to correct for the turbulent distortion of the Earth's atmosphere in order to remove the light of the star. So here we usually rely upon some kind of post-computational analysis, such as principal component analysis or CLIP. So one uses an adaptive optics system to make as close to diffraction limited images as possible. So these are examples from the Magellan adaptive optics system that I have most used. You might take a stack of these images, hundreds or thousands of these images, and then you use an analysis that looks for the commonalities between that the images in that large stack. So anything that changes, for example, a disk rotating on the sky as the telescope tracks it, doesn't come out in that principal component. But as you can see, these are the first 5 principal components from an analysis of a stack of images. And you can see the first component contains most of the structure of the point spread function, what the telescope plus adaptive optics system are doing. And then there are sort of tunings on that in the subsequent components. So now you can subtract the right fraction of each of these components from your image to reveal the disk. So I'll just show you that this actually works. Here's an image taken with the Hubble Space Telescope using that reference star subtraction technique that I showed you first. And here's an image of the same disk. You'll recognize this HR 4796 if you happen to be in one of the groups doing that for your hands-on workshop this afternoon. And here's that same image taken at a slightly longer wavelength with the Magellan adaptive optics system using that principal component analysis removal. So that's how we actually observe disks in scattered light. So the second main way that we observe disks is through their thermal emission. So here's another image of our sky where you can again see the zodiacal light, the light in our system. Here you see the plane, we're in galactic coordinates, you see the plane of the galaxy. This is dust that's heated by young stars mainly. And here you see the dust along the ecliptic, the dust in our solar system. And the wavelengths are color coded here. So blue means emitting primarily at about 12 microns. This is from IRAS in the infrared. So the dust in our system is primarily seen near the Earth. And so it is absorbing light from the sun. It's heating up. It heats up at the distance of 1 astronomical unit to about 300 Kelvin. And then it re-radiates at the wavelength characteristic of that temperature, which is about 10 microns, 12 microns. So you can add up all the light in our emitted by our zodiacal cloud and compare it to the luminosity of the sun. And that is the metric that we normally use to say how dusty a disk is, the fractional luminosity, the ratio of its infrared luminosity to the stellar luminosity. So for the solar system, that's 10 to the minus 7. It's very small, and that's at the limit, basically, of what we can detect in any other system. The really cool thing about this as a tracer of planetary systems, though, is that that's actually very bright compared to the amount of mass in the system, right? So our zodiacal light has maybe a trillionth of the mass of the planets in our system, but it has 100 times the infrared luminosity. So it's actually a very good tracer of the fact that a planetary system exists, or at least planetesimals exist. So for the first time this infrared excess was detected around main sequence like star by the IRAS satellite as infrared excess. And the big advantage of the thermal infrared excess is that the star is faint, right? It's falling off on the Rayleigh-Jeans tail here, like 1 over lambda squared. And so if it has dust that's emitting strongly at far infrared wavelengths, like here in Vega at 60 and 100 microns, it's quite easy to observe above the background of the star, unlike in the scattered light case. So you can add up all that light for Vega, and you see that it amounts to about 10 to the minus 5 fractional luminosity. So about 2 orders of magnitude larger than our solar system at a temperature of about 50 or 60 Kelvin. So that means that it's out at distances akin to the Kuiper belt. So now you've looked at spectral energy distributions for a couple of days, and you know that if you're observing in the far infrared, where it's easy to distinguish the disk from the star, you're basically looking at cold dust out at Kuiper belt-like regions. Whereas if you're looking at warm dust that gets a little bit harder to distinguish from the star, you're looking more on astronomical unit scales at a few hundred to 1,000 Kelvin dust. So in order to find this warm dust that Mark also talked about in his talk as being perhaps indicative of comets coming in or planets perturbing a system, you need to actually resolve this dust from the central star, because this amount of infrared excess is often not detectable above the background of the star. And so to do that, we need interferometry, because we're working at long wavelengths, and we need to synthesize the diffraction limit of a large telescope by using multiple smaller telescopes. So in the mid-infrared, the premier instrument for doing this has been the Large Binocular Telescope Interferometer, working at about 10 microns. And of course, in the far infrared and submillimeter, the premier instrument is ALMA, working at a few hundred microns to several millimeters. So this is the compact array, actually, when I visited it a couple of years ago. So in the far infrared, you cannot just then detect the disk through its spectral energy distribution, but you can actually image the emission of those cold dust grains. In this case, we're looking at emission at 1 millimeter from the AUMIC disk. Now, I wanted to point out one thing here. Note that it does appear like the star was appearing in this image, even though if you look at the spectral energy distribution of a really low mass star like AUMIC, you expect a very, very small amount of far infrared emission. What you measure is considerably above that expected photosphere of the star. So you cannot immediately assume in this case that all of the excess is actually from a disk. It might be from warm dust near the star in an asteroid belt. But as is actually the case for AUMIC, it really is the star. The star is emitting millimeter radiation, not from its steady state photosphere, but from stellar flares. And this is a particular problem for these late type, these M stars, low mass stars, which flare throughout their lifetimes. So that's one confounding factor if you're actually using infrared emission to find a disk. Okay. So now you know how we find disks. Let's talk a little bit about the occurrence rates of debris disks. So the best way to do occurrence rates is to do a volume limited survey. So go to all the stars nearby the sun, look at them with a sensitive infrared telescope like Spitzer or Herschel. We've had 2 great missions in the last decade, and actually measure how many of them have infrared emission from disks. And when you do that, you find that about 22% of the stars in the solar neighborhood have cold debris disks. So these are things with typical temperature of 50 Kelvin, a typical size of about 50 astronomical units, and all with more dust, at least an order of magnitude more dust than in our solar system, because that's what could be detected even with these very sensitive missions. You'll notice that there's a little bit, though, of spectral type dependence. And so the late type stars, the M stars, have a lower overall incidence, and there are a lot of them. So they reduce the overall incidence of debris disks in the solar neighborhood. But still, there are a lot of debris disks. So a lot of stars reach the main sequence and reach old ages with enough dust that we can detect it. That indicates that they might have a planetary system, even if we can't actually detect the planets directly. So that
Alycia?
yeah.
So if you could speed up a bit, so because we only have 4 minutes left for this
Okay.
session, and
I'm
we would like
almost-
to take some questions if there are any.
Okay.
Thank you.
So you can also do this for exozodiacal dust, and the statistics aren't that different, but most commonly you find exozodiacal dust where you also have cold dust. So now the main part of the talk that I have online is about imaging the structures from planets, and you can go and look at it, but I just wanted to point out that we image all of those different structures that Mark talked about. So warps, cavities, eccentricity, gaps, wings, warm dust that might be signposts of planets. And you can look at the online version to learn more about this. And finally, I just want to mention 3 things very quickly, which is that there are 3 other attributes of debris disks that you should know about. One is that they often are gas poor, but they are not gas free. And it appears that the gas and the dust are generated from the same location. And so we assume then that it's comets that are generating both the dust and the gas. Second, there are some really interesting extreme objects that we call extreme debris disks with very high fractional luminosities, warm dust, silicate emission features, and can be seen around old stars, binary stars, and are highly variable. So this is telling us something really interesting about the persistence of planetesimals and how they can be disrupted over time. And third, that we can learn a lot, as I said at the beginning, about the composition of systems from looking at all the different ways we can observe the disks. So there are lots of different ways of measuring the composition, and I go into those a little bit more in a full version of this talk. So I'll just conclude by saying that debris disks may be as common as planets. We mainly detect the bright ones. Their structures hint and sometimes scream at the presence of planets. And because planets and disks evolved together to form a mature planetary system, debris disk compositions and evolution have a lot to tell us about how planetary systems evolve over time. And I will stop there. Thank you.
Great, thank you so much to both of you, Mark and Alycia. Everyone, please put your questions in the Q&A or in the Slack channel. We have 2 minutes left. So there is one question in the Q&A referring to disks near our solar system, which I believe are also the best to study, right? So if you want to comment on some nearby disks.
Right, so the disks, the stars that are closest to us, of course, the disks appear largest on the sky if they're all intrinsically the same size. That doesn't necessarily make them the easiest to study, but some of the best known disks really are around very nearby stars like Epsilon Eridani, Fomalhaut, Vega. Beta Pictoris is one of the youngest, nearest stars to the sun. So you do get a lot of information about those disks, but they tend to be very big and so actually very difficult to image.
Okay, I don't think there are any more questions, but I would be happy if you let me ask some. Yeah, so can you comment a little bit on the size of the disk with respect to the spectral type of the main star?
Yeah, there's a little bit of a dependence on the spectral type of the star. And some of that may then have to do with how more massive stars have planetary systems that evolve somewhat further away from them. Some of it is an observational effect, but some of it may be a real effect about how fast material orbits the star and therefore how fast the disk evolves. Maybe Mark would say something more about that.
Yeah, well, there is a correlation, right, with disks looking like the ones that have been resolved are larger around higher mass stars and smaller around lower mass stars. But like Alycia said, some of that is observational bias. But the location where they are could be linked to snow lines, potentially. But I think we need more observations to tease out what's going on. And the ones that are closer in, you would expect to collisionally deplete. So that's one. From a theoretical perspective, you don't expect to see very close in disks because they collisionally grind themselves away. So by the time you're looking at a star that's giga years old, you wouldn't expect to see an asteroid belt because it would be too faint.
Yeah, so if you have a very massive disk, is it more likely to build more planets or more massive planets?
Good question. I mean, if you see a more massive disk, then it's got more mass it's likely to have more mass in planetesimals. And if it had more planetesimals, then maybe it formed out of a more massive protoplanetary disk, which may have gone on to form planets as well. And we've got examples where we know that there is a correlation in, for example, HR 8799 that does have a massive debris disk, and it does have very massive planets. But obviously that's not a one-to-one correlation that works for every single disk.
Yeah, actually, there are not many debris disks with known planets, right? Is that right? An observational bias? Is it because they're around very bright stars and it's hard to do direct imaging, or is the disk interfering somehow in the detection?
So I do talk about the incidence of debris disks and exoplanets in my longer version online. And actually, there are a fair number of debris disks and planets known in the same systems. And it does appear like there is a positive correlation. So you're more likely to have a cold debris disk if you have a far out giant planet, where there appears to be no correlation between close-in planets, the kinds that are discovered through radial velocity or transits, and the presence of an outer debris disk. But it is fairly common to have a wide gas giant planet and a debris disk.
Yeah, the problem is it's small number statistics, because we've got 20% of stars have got debris disks, and 5–10% have planets. So that it's hard to tease out those correlations without large numbers of looking at large numbers of stars.
Yeah, and so there is one new question in the Q&A. It says debris disk structures thus point to the presence of exoplanets. Liran Kushner proposed a dynamical instability that can reproduce rings found in systems such as HD 141596698. Have any observations found planets around based on debris disks?
So there are observations of disks around of planets in debris disks. One has not been found in HD 1415669. So yeah, the problem with pointing to planets, I think Mark would agree with this, is that sometimes the solutions, and Jehan talked about this too, are not entirely unique, right? So there are other ways of forming structures in disks, often, and including gas is one of them, without just the type of planetary perturbations that Mark talked about. But HR 8799, Beta Pictoris, like both of those are examples of debris disks with different structures, one with a warp, one with a very big inner cavity, that are probably explained by planets. The planets have been directly imaged in those disks.
Okay, and one last question. Oh, sorry, go ahead, Mark.
No. If there's another question, we can take it.
Okay, one last question we can take. Do observations of this correspond in majority of solar-like stars rather than massive stars?
The majority, well, it's about 20% across the board of whether you have a detectable debris disk. They do appear to be slightly more massive and brighter around A-type stars. So there's a slight trend towards disks being more detectable around A stars and less detectable around M stars. But my guess would be that they're equally common around all types of stars. It's more a detectability issue.
Okay, thank you very much to both of you. I think we can now move on to the next session, which is the panel discussion about this dispersion. And so the speakers are Andrea Banzati from Texas State, Adam Kraus